actually illuminating the whole thing, even though you can't really see it. And we can also look at it in much higher frequencies, which are X-rays, and it looks a little more enlightening. That's the pulsar in the center. These rings are sort of the electrons that the magnetic field is causing to be flung out. And here, these jets are where the radiation and a load more matter is coming from. So the pulsar, in the sort of model of it, looks something like this. There it spins the magnetic field there, and the radiation beams coming out like a big lighthouse, sweeping past us and giving the regular pulses that we see. Now, they're actually best observed at a much lower frequency, which is the radio. And we use big radio dishes like the telescope at Jodrell Bank to look at a pulsar. We can't really make an image, but we can see pretty much what we saw before. There's the main pulse going off, and then little pulse in between, and that just repeats over and over again. And the clock-like accuracy of them is better than pretty much any clock on the Earth except for an atomic clock. Now, I know I'm running out of time, so I'm going to have to go a bit more quickly.
Carry on with density bit,
Okay, right. I forgot to mention this. The Lovell telescope is about as big as 500 million bowls of cereal. The density bit. Oh, it's very dense, this neutron star. Well, okay, even if this is the last thing I get to say. The neutron star, as I said, it's bigger than the sun. It's about 1.5 times the mass of the sun. It's all crammed into a radius of about 10 kilometers, and that gives it a density of about 500 million Tyrannosaurus rexes per teaspoon. It's a silly unit for a silly number. In any kind of everyday units, this is just pretty much unimaginable. It's like 10 times the population of the Earth crammed down into that kind of space. So it's a really extreme environment. And if I haven't completely run out of time, I'll carry on and tell you why pulsars can kill you if you get too close. Luckily, there aren't any close to us. They have a magnetic field that's about equivalent to 100 billion fridge magnets, which is a lot. That's rather strong. And that thing rotating is flinging out all these charged particles from the surface of the neutron star, and they're going to, well, the technical term is ablate you, which means smash you to smithereens if they hit you. If you did get to the surface of the pulsar, you'd then find it was 1,000,000 degrees Celsius, so that wouldn't be very conducive to life. And its main frequency of light that it's giving off due to all this heat is actually X-rays, so it wouldn't even show up in the visible range much at all. I tried to work out how many naked airport scanners it was equivalent to, but I couldn't. The gravity of the thing is also going to stretch anyone that comes too close, like so. And the reason for that is because there's so much mass in such a small space. If you get close to it, going head first, then the gravitational force on your head is going to be a lot more than what's on your feet. And this technically is called spaghettification. That's not made up. Am I out of time? I'm going to go on. So they're not something you really want to be close to. And one of the things I wanted to say was what we can use them for, because obviously astronomers like to study these things. And to do that, I have to introduce a slightly strange concept called gravitational waves. Now, in Einstein's theory of relativity, gravity is the curvature, bending of space. And it also predicts that certain events like black holes going around each other and things like that should release sort of ripples in space-time, which are these gravitational waves. And they propagate outwards just like a wave. This is what a gravitational wave would look like if it arrived at Albert Einstein. He looks delighted that he's made that discovery. It moves along and it stretches and squashes the space as it does so. Of course, that's a massive exaggeration, otherwise we'd probably see them all over the place. They're incredibly weak. They're really just theoretically predicted. No one's ever detected them, but we think we can do this using pulsars. And this is what we're trying to do at the moment in my research group. These pulsars, we can time when their pulses arrive very accurately. And so if a gravitational wave comes along and changes the path length of the signal as it comes to us, and that's what these yellow lines represent, then we should be able to pick that up. And the reason we're looking at a load of pulsars all over the sky is we want to see how it changes all the pulsar signals in the same way at the Earth. That's the component that we can actually pick up, and we're hoping to detect gravitational waves right here, which should be all around us right now. It's something that no one's ever done. And this bit I probably better had to skip over quite quickly. These are other things called pulsar. There was a car in 1985. It seems to have inspired a lot of futuristic things in the 70s and 80s. A car, and the Nissan Pulsar manages 6,000 RPM in its engine. The fastest pulsar spins at 40,000 RPM. But that has recently been matched by a toothbrush called the Pulsar. Meanwhile, the first ever digital watch was also called Pulsar, and it had an accuracy of about 1 second in 10 days, whereas pulsars spin with a predictability of about 1 second in a million years. And last of all, the last thing I wanted to show you that was called Pulsar is a French progressive rock band, which I didn't know about. They were fronted by Rolf Harris in a dress. And illustrated a fairly common misconception about pulsars. They said that their name was derived from the dark sun, which can be found only by the sound waves it emits. In fact, pulsars don't emit sound waves, they emit radio waves, which are a type of light. But you can turn this into a sound wave. And the fastest pulsar, or the second fastest pulsar, I think, actually is fast enough to make a tone, and it sounds, if I can play it, this. Great. I don't think I can play it. It's not really that important. It sounds like an angry gnat. And it's definitely not as good as the rock group pulsar. It's actually one of the most irritating sounds in the galaxy. So that just goes to show that pulsars shouldn't be listened to, but looked at. And since I've overrun my time by about a factor of 2, I'll